In this lecture, we will solve a numerical example concerning the Poisson's equation, which we have seen in our previous lecture. So let us see what is the example. We are given that there is a uniform charge density, which is spherically uniform. So this sphere is having uniform volume charge density, and this sphere has a radius of b, and for radius between 0 to b, the charge density is given as minus rho naught. That is, it is a constant equal to minus of rho naught, where rho naught is a positive constant. That is, rho naught is positive and the charge density it implies is negative. Now what we need to find? We need to find the electric field as in the inside of this sphere of uniform charge density, as well as outside this sphere. That is for both cases. That is when r belongs to this 0 to b and when r is greater than b. We need to find electric field by solving Poisson's equation or Laplace equation, whatever the case. We have solved the similar numerical example using Gauss law. Now we are asked to solve this using Poisson's and Laplace equation so that we can see how to utilize these equations. So first we will solve the case when the point is lying inside this sphere. That is, let us say this is at distance r from the center. That is, 0 is small or equal to r, small or equal to b. So we know that rho is equal to minus of rho naught. And it implies in this region, Poisson's equation will be applicable. That is, del square v is equal to rho naught by epsilon naught. Now there is one thing to note, that this is having spherical symmetry. So there is no variation in theta direction as well as phi direction. So we are going to deal with only the variations in the radial direction. So we will use the radial form of the Poisson's equation, which we have derived in our previous lecture, and we will take only the radial part, 1 by r square d by, now this partial differentials have been changed to the full differentials, d by dr r square d by dr, and I will write it as v equals to rho naught by epsilon naught. So this r square can be taken to the right hand side by cross multiplying for both sides. D by dr r square dv by dr is equal to rho naught by epsilon naught r square. Now we will integrate once. So what we will have, r square dv by dr is equal to rho naught by epsilon naught r cube by 3 plus some constant c1, or in different form we can write it as dv by dr is equal to rho naught r over 3 epsilon naught plus c1 by r square. Now we know that E is equal to minus of del V, and since there is only the variation because in the radial direction only, so this gradient will have only the radial component in it and other components will be 0. So I can write it is equal to minus of AR dV by dr. So it implies field is equal to minus of rho naught by 3 epsilon naught AR plus C1 by r square AR. Now we know that field cannot be infinity when r tends to 0. This term we should know that it has come because this step which we did in this slide, where we cross multiplied by r square on both sides, was not exactly mathematically legal. So this is the term which we are going to bear with. But since we know that the field is not going to be infinity for uniformly charged sphere at its center, so for this to happen, this C1 should be equal to 0. So we see that the field inside will be equal to minus of rho by 3 epsilon naught r AR. I forgot to write r here. So this is the electric field, and which is same what we found in one of our previous lectures by using Gauss law. Now we will find the field when we are outside the spherically charged sphere. Now here rho is equal to 0, so we will use the Laplace equation. Again, we will use only the radial part because there is radial symmetry and there is no variation in theta and phi. So this is total differentials now instead of partial differential. So we will again do the same thing. We will integrate it once. So it will give us r square dv by dr is equal to some constant c2. Now it implies dv by dr is equal to c2 by r square. Now we know that electric field is again is equal to minus of del v is equal to minus of ar dv by dr. So we know that it comes out to be minus ar c2 by r square. Now we need to find this constant c2. How to do that? As we have seen that there is no discontinuity in the medium, so we do not expect any discontinuity in the electric field itself at the interface where this sphere ends. Here medium is again epsilon naught, here it is also epsilon naught, only the difference is that there is source charge density in this sphere. So at this place the electric field will not have any discontinuity and it should be equal, and the equality should be given by both of these formula. So C2 over R square should be equal to rho naught over 3 epsilon naught. R is equal to B here and this is also equal to B here. So C2 comes out to be rho naught B cube over 3 epsilon naught. So we see that the electric field is given as minus of AR rho naught B cube over 3 epsilon naught R square for R greater equal to B. So in this way we have found electric field using the Poisson's equation and the Laplace equation and their methods of solving them. Now if we want to find the potential, we can easily find. We have seen that dv1 or inside was dv by dr equals to rho naught by 3 epsilon naught r, and the constant c1 was 0, so it was 0. So we can find out by again integrating. V is equal to rho naught by 6 epsilon naught r square, then again some constant c3. Now we need to find this constant c3. Sorry. Now let us see how to derive that. For that, what we will do, we will derive the potential using the second equation, that is this case, and we will put the value equal at B, R is equal to B. So from this we will again integrate and we will find, let us write it again, dV by dr equals to C2 by R square, where C2 was equal to rho naught by 3 epsilon naught. Now we will integrate it. So V outside is equal to rho naught by 3 epsilon naught B cube 1 by R, and minus sign will come here now, plus some constant C4. Now although it appears that we are again in some problem because this C4 we don't know, but we know that when this R tends to infinity, this potential should fall to 0. And if it is to happen, it implies that this C4 should be equal to 0. Otherwise, we will have a constant potential, which is not possible. So for this finite spherical charge volume, we have to get this C4 equals to 0. So we have V is equal to minus rho naught B cube over 3 epsilon naught R for R greater equal to B. For R equal to B, this will become V is equal to minus rho naught B cube 3 epsilon naught B over minus rho naught B square over 3 epsilon naught. Now from this we can find the this constant C3, and by equating these two, we are going to have C3 equals to minus of rho naught B square over 2 epsilon naught, and the value of the potential inside when R is smaller equal to B, this 0 is smaller equal to R, will be equal to minus of rho naught over 3 epsilon naught 3B square over 2 minus R square over 2. So you see that this is again the same equation which we have seen in one of our previous lectures, and we found out using integrating by first finding the electric field by Gauss law, and then we found this potential by integrating this electric field. But here we have directly solved the Poisson's and Laplace equation to find this electric potential. So in this way, we can find the electrostatic field as well as potential if we know how to solve these Poisson's or the Laplace equation, as the case may be. In very simple geometries and very simple cases, it is quite possible to find the analytic solutions of this equation. However, somehow it may be very difficult to find the solution, and we may need to resort to numerical methods also. Now there is a theorem which is valid, and that theorem is uniqueness theorem. We will study in the next lecture, and that will give us hope in solving these kinds of equations. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel and join us in our Telegram group, whose link is given in the description of this video. Thank you.